Thank you for inviting me to present at the 2020 AIChE annual meeting. I'm 287e-Reckamp, a senior analytics engineer with Seeq, and I'll be presenting on why collaboration is so critical for effective deployment of data analytics. During the presentation, we will start at looking at how manufacturing data has evolved over time, look at expectations and realities of big data analytics projects, and then focus on two use case applications while stressing the importance of collaboration, before finishing out with some conclusions. When we look back at the evolution of data and data analytics, it all started decades ago with manual recording of data from process manufacturing plants. As technology evolved, so too did this manual data entry, replacing it with electronic data collection that automatically recorded sensor values into data historians and databases at a periodic interval. While this type of data has been stored for 1 or 2 decades, manufacturing plants have received little benefit from the data beyond simply trending that data set. However, as computer technologies continue to advance, there now exists an opportunity to leverage data analytics tools and algorithms on this vast array of valuable data. Ultimately, the goal of data analytics is to improve outcomes for the business by improving the costs, time, quality, or consistency of the manufacturing process. In order to achieve that goal, the data has to flow quickly from the sensors to the entire organization, from the operations floor all the way up to roll up key performance indicators or KPIs for executives and managers. Improvements in the business outcomes require teamwork in between, including collaboration from operators with hands-on experience, engineers with process knowledge and expertise, maintenance personnel with information about the equipment, data scientists that have a deep understanding of algorithms and analytics, and plant managers that prioritize and drive the right manufacturing efficiencies. When most people think about data analytics projects, the expectation typically looks like the view here. Most people think we have some data stored over the last decade. Let's bring in some data scientists, give them access to that data, and let them apply algorithms on that data set. From there, we want to visualize the results, and those model results can be published for the operators or engineers to see and act upon. However, the reality of data analytics is that those two blue arrows encompass a large amount of work and infrastructure requirements by the organization. When we think about the reality of those blue arrows, we can see that there's so much more that needs to be considered. In order for the algorithms to be applied to the data, there's a number of data preparation steps that need to be undertaken. For example, things like accessing the raw data, aggregating data between data sources, aligning and interpolating data, removing noise and outliers, adding process context, and understanding multi-collinearity between variables. This entire process requires collaboration between the data scientists and the subject matter experts that have the process knowledge in order to prepare the data for the algorithms. It's important to remember that the model results are only going to be as good as the data feeding the model, so data preparation should be focused on just as much, if not more, than the algorithms themselves. On the other hand, after the algorithms have been selected and applied to the data, there's a significant amount of work and infrastructure required to operationalize the models and algorithms. In order to apply these models to make decisions on the data quickly, these algorithms need live connections to the data. The data preparations need to be automated, and the algorithms need to be executed online and near real time. Then, as much as we'd like the algorithms to be optimized the first time, there's usually a feedback loop of refinement that needs to be done on the models over time, retraining or tuning those models for new production observations or scenarios that are based on SME feedback. In addition, these models require subject matter expertise to understand what actions to prescribe based on the model results. Ultimately, data analytics is an iterative process. It starts with the identification of a problem or opportunity for improvement. You then dive into the data, perform analytics, publish the results, and sustain the analytics. And that continues to adapt and adjust to changes in the manufacturing process or new problems that may be observed. These analytics result in value for the organization in the form of manufacturing improvements such as reduced downtime, increased production rates, and optimized product quality. Now that we've talked a little bit about the data analytics process, let's jump into a couple of use cases that showcase this collaborative environment to generate value from the data analytics. In this first use case, we'll look at a bearing failure prediction model. Bearings typically fail exponentially with little notice, making it difficult to schedule maintenance ahead of time. Also, a failure in one bearing can subsequently result in failures in other bearings inside the system as well. In order to model and predict these failures, we'll show how machine learning algorithms such as an artificial neural network can be deployed to detect anomalies in the process data. As an example of the results that can be achieved on these models, one company found that they were able to notify of abnormal operations several days before a bearing failure, enabling the maintenance team to grease the bearings to prolong the life of the bearing, order parts and minimize costs, and to proactively schedule maintenance downtime, which resulted in savings on the order of $500,000 per outage. Truly understanding all the aspects of this data set requires a collaboration between engineering, maintenance, operations, and data science. Each of these team members brings something different to the analysis of the data. For example, the engineer brings knowledge of process changes, potential failure modes or an FMEA of the equipment, and the information around what data is considered normal operation versus abnormal operation. The operations staff brings process observations, and after a failure can help provide visual evidence for root cause analysis of the failures. The maintenance staff brings information around when the last maintenance event was performed on the equipment, the preventive maintenance schedule, and knowledge of what other pieces of equipment operate similarly to either include in the data set or to also apply that same analytics to in order to derive even more value out of the analytics. And finally, the data scientists have a deep knowledge of algorithms and data analytics techniques such as cleansing, modeling, and visualizing data. However, these often have limited process knowledge or expertise and rely on those other team members for information in order to best select the algorithm of choice or provide context to that training data set. So let's look at this in practice. The raw vibration signal for the bearing is a green time series signal at the top of the graph. However, before this can be put into the model, we need the rest of the team to provide information about the data set. For instance, the maintenance team may provide context as to when the equipment was down for maintenance. The operators may provide some context as to when normal operation is, avoiding downtimes for maintenance events or other reasons. And the process engineers may take all that information and provide some data cleansing methods, like removing the data during downtime or applying a filtering algorithm to remove noise in the data set. And finally, all that knowledge and information can arrive at the data scientists, where they can discuss the best method for predicting failures in the future. In this case, due to the exponential rapid increase in vibration data, the data scientists selected a classification algorithm by way of an artificial neural network. This determines whether the data is indicating normal or abnormal operation mode. In this case, you can see the result of the model in the red signal at the bottom, where 0 represents normal and a 1 represents abnormal operation. And you can see how the data shows an advance notice to the maintenance and operations teams about the abnormal operation prior to the failure event, providing time for scheduling that downtime and ordering parts for the maintenance prior to failure. In addition, with knowledge from the rest of the team, they were able to apply the same analysis to multiple pieces of equipment that had similar setups and sensors as shown in the bottom right visual, where it is actively monitoring artificial neural networks on the various areas of the plant that indicate where bearings are showing problems in red. This knowledge of the plant enables a much larger scaled approach to getting value out of each data analytics model. So as you can see with this first use case, the data analytics process requires a team to solve challenges. In addition to the data and algorithms, solving a challenging problem often requires cross-functional collaboration between groups such as engineering, operations, maintenance, and data science. Each of these functions brings their own expertise to the problem statement, where collaboration between these various personnel will result in the best solutions to derive performance outcomes. It's also important to consider the model outcomes. Ultimately, each data analytics solution should derive some value to the organization, which should be able to be summarized through appropriate visuals or roll-up KPIs to show improvements to the bottom line for managers and executives. In 2020, we hit another challenge for data analytics. Prior to the pandemic, we typically saw these cross-functional teams co-located at a site where engineers, operators, and data scientists could interact in person. They could have hallway conversations and even tour the plant to visualize the challenges. However, as a result of the pandemic, while operations and maintenance are still typically on site, engineers, data scientists, and managers are often distributed working from home. This requires the team to rely on audio and visual conferencing to communicate and collaborate to solve the problems. We now have to think about how we can bridge the gap between the in-person communication patterns and this new distributed work environment. Optimizing the collaboration between the distributed team may consist of the shown capabilities on this slide. For example, when performing data analytics, it's highly important to document the analytical steps so that others on the team can understand the analysis and add their own commentary. In addition, the operations staff on site should be able to annotate and record events to provide context to the data in near real time, and those distributed employees can then utilize that context to drill down into the data set itself. In order for all these various personnel to work together, there should be a Google Docs type environment where multiple users can simultaneously add information and perform analytics and share with the rest of the organization. And finally, the analytics should be set to be live updating to make data-driven decisions in near real time for the entire team, from the operations staff all the way up to the executive level. These capabilities make for a data analytics infrastructure that will enable effective collaboration across the team to derive the most value for the organization. In the second use case, we'll take a look at filter membranes and the long-term degradation or fouling of the membranes that can result in increased cycle times, lost yield, or poor product quality. In this scenario, we're going to leverage first principle equations to simplify the set of variables to a single membrane resistance value, and then build a predictive model based on the resistance trends over time. In this case, we'll extrapolate the trends into the future to determine the optimal maintenance period and establish warning and alert limits around that. Companies applying this technique have observed improvements in cycle time, yield, and batch quality from predictable membrane performance. In addition, utilizing data-driven condition-based maintenance strategies have maximized filter lives while minimizing downtime. For this use case, we first want to understand the problem. It is known that filter membranes degrade over time and can lead to downtime or failed batches. However, the rate of this degradation can change based on a number of variables, such as the specific processes being run, process parameters like temperature, flow, pressure, or even solution concentrations, and even the filter type. In order to minimize unplanned downtime, the maintenance staff needs some sort of advanced warning of impending failure to schedule that maintenance. Analyzing this problem then starts with the data. This includes various signals such as flow rates and pressures on each side of the filter, some batch context to compare equivalent periods of time, the products or grades being run, or even information about historical failures that may provide information for the desired warning and alert limits. We then can move into the modeling section. In this case, the process engineer or subject matter expert may know that instead of trying to build a model on all 6 of the signals, which includes flow rates and pressures around the filter, that all the signals are interrelated into a variable known as membrane resistance, which can be calculated by first principles equations for Darcy's law. This valuable expertise simplifies the data set by utilizing the process knowledge of the subject matter expert. Once the model is set, the resistance value can then be regressed based on time and extrapolated into the future to determine when the resistance is expected to cross warning and alert limits set based on historical failures. They can then be used to notify the maintenance staff. In order to verify this is the best model, the model can be compared against other algorithms by the data scientists, which ultimately found that the Darcy's law regression method was the best method for this modeling. Again, this use case takes a cross-functional manufacturing team from operations, maintenance, engineering, and data science to effectively deploy the data analytics model. In summary, I want to leave you all with 2 key messages. First, data analytics involves much, much more than just the data and the algorithms. In order to deploy effective data analytics models, an organization needs to focus on the data preparation phase, as well as making sure the infrastructure is in place for operationalizing the models with low latency and automated processes. In the deployment, there are lots of human interfaces across cross-functional manufacturing teams. Secondly, collaboration is critical for effective analytics. Building the best model requires more than just the algorithm. It leverages the knowledge of the cross-functional team to be captured and the data, model, and visualization results to be shared across the organization to enable the feedback loop to continually improve the model as new information and data becomes available. After working with numerous companies on deploying analytics, I can attest that collaboration is commonly the most important factor that is overlooked when companies attempt to leverage the most recent technological advances in data analytics. And with that, I would like to thank you for listening to my presentation today. If you have any questions, please feel free to reach out to me at either of the emails provided on this slide.